So, good morning, everyone. Today we have the pleasure to receive Professor Koenraad Kuijken from Leiden Observatory, and he's going to talk about weak lensing and the KiDS survey and cosmology applications of it. So thank you very much for accepting this invitation, and please go ahead.
Thank you very much. Can you hear me?
Very well.
Okay. So I have a talk which is probably something like 40-45 minutes long, and I'm happy afterwards to take questions, or also in between. I don't know how easy it is with the system, but if people would like to interrupt and ask questions, then that's fine by me. So what I would like to describe today is some recent results on the cosmological model based on weak lensing measurements from the kilodegree survey, or KiDS for short, which is one of a number of large weak lensing surveys that are ongoing at the moment from the ground. So I'm sure you've all heard about the dark energy survey, but there are several other surveys which are doing the same thing. So I'll start with a brief review on what weak lensing surveys are good for, what are their strengths, what are the difficulties, and then I'll go on to interpreting the results and describe what we found with the KiDS survey ourselves, and then a little bit about the future at the end. So a little bit of motivation. I'm sure this is not new to many of you, but so this is the cosmological model as we have it at the moment. It's, on the one hand, a very successful explanation of the whole history of the observed universe from the very, very beginning all the way to the present, and it's basically an application of the physics that we know over an incredible range of time scales and length scales. There's many different observations which all seem to fit within this picture, from big bang nucleosynthesis to the CME measurements to large-scale structure. And while on the one hand this is a fantastic success, on the other hand, of course, it's also a little bit embarrassing because we've had to invoke at least three very mysterious processes or ingredients. One of them is inflation to get the initial conditions that we see. One is dark matter to explain the large-scale structure. And one is dark energy to explain the accelerating expansion of the universe. So it's on the one hand a very simple model, on the other hand it raises many very fundamental questions about physics. And those are the focus of many of these cosmological surveys that are now trying to learn more about this. So here's an illustration of the precision aspect of it. This is the Planck map. On top of it is the angular power spectrum, and the fit through it is the standard lambda CDM model, which is, simply explains all the data with a simple 6-parameter model in glorious detail. So this is why we talk about precision cosmology. It's also a fantastic resource because we can use it as initial conditions to calculate what the universe should look like today. So if you interpret the cosmological, the CMB, you get very clear predictions, very accurate measurements of how much dark matter there should be, how much dark energy there should be, and how many baryons make up the total picture. So this is this famous pizza diagram from the Planck collaboration now. And what we can do with that is we can make simulations where we put these ingredients in a computer and try to simulate whether the initial conditions that we see in the CMB would grow to something like the large-scale structure of galaxies that we see today. And so if you do this exercise, I hope this little movie will work across the connection. If you take one of these cosmological simulations and you put them in an expanding universe and let the particles gravitate under each other's influence as well, then you see very nicely these competing effects of the expansion on the largest scales, but the contraction and the gravitational instability where dense regions get denser and denser as a result of self-gravity on smaller scales, basically cluster scales and smaller. And so this gravitational instability picture is a very natural, very generic consequence of the lambda CDM model. And what's really amazing is that if you compare this kind of structure with what we measure in the galaxy distribution today, you can look at the detailed statistics of the clustering, and it fits remarkably well. So this is all part of this great success story. This is why this lambda CDM model has lasted as long as it has, and is still our standard model. Now, one of the issues is that when you look at galaxy surveys as a tracer of the large-scale structure, then you have to take account of biasing. The galaxies do not necessarily follow the distribution of all the dark matter, because there may be some places where there is not enough of a mass contrast for galaxy formation to kick in, or there may be all kinds of other feedback processes that inhibit galaxy formation on various scales. So this biasing of galaxy formation makes it very difficult to get a detailed quantitative picture of the clustering of matter. And so we're looking for other techniques, and one of the most promising techniques is gravitational lensing, which is the effect of light rays being deflected by mass concentrations, and that is simply sensitive to gravity of all the matter. It makes no distinction between baryons and dark matter. And so gravitational lensing, in principle, has the power to trace the full large-scale structure of all matter, and therefore make a much more direct comparison with these predictions from the cosmological model and the kind of simulations that I just showed you. So this is an effect which has now been observed for a couple of decades. What you see in this box is a simulation, or not even a simulation, it's a sketch of what happens to distant galaxies that we observe through a whole volume of this inhomogeneous gravitational field due to large-scale structure. And you see that the light rays make a kind of random walk as they come towards us. On average, so the effect is much exaggerated in this picture. On average, a typical light ray from a distant galaxy is deflected by about 3 minutes of arc. So it's a significant effect. In principle, it's very measurable, but it's also not, it's still very much in the small angle approximation, which makes the calculations a lot easier than they would otherwise have been. And so it means that when we look at the distant universe, we really are in some sense looking through a bad window, an old window, which is distorting our view of the distant universe. And so what you do in gravitational lensing is try to figure out how strong this distortion is, and then use it as a way to measure the amount of clustering of the matter between you and the distant universe that you are imaging. So as I said at the beginning, there are now 3 weak lensing surveys ongoing. These are massive projects with hundreds of telescope nights invested in each of them. And these 3 projects are the Dark Energy Survey, the Killer Degree Survey, and the Hypersupreme CAM Survey. They're each covering over 1,000 square degrees. DES is covering the largest volume, the largest area, and Hypersupreme CAM is going a lot deeper, and KiDS is sort of in between in terms of area and depth. So the depth is similar to the DES depth, the area is similar to the Hypersupreme CAM depth. They use different telescopes, different optics, different observatories, so comparison between these 3 different surveys is also a very good way to make sure that all the systematics are under control and not driven by the properties of one or other instrument. And so you see various other comparisons between the surveys in this table here. One of the special things about KiDS I can mention is that we have a total of 9 photometric bands, because we are not only observing in the optical but also in the near infrared using the VISTA telescope or next to Paranal. So in total we have 9 bands from the U band to the K band, which we feel will allow us to do more stringent tests of photometric redshifts than some of the other surveys that use fewer bands. Okay, so a little bit about what makes weak lensing so powerful and so promising, and why have people been working on this for decades now. And the reason is really that it's fundamentally a very simple diagnostic. You measure the total projected gravitational field due to all the matter. You don't care what causes the gravitational field. And the deflection is a very simple geometrical thing to work out. It's very simple 2-dimensional potential theory to go from a distribution of mass to a predicted distortion on the sky. And the signal that you're looking for is that around any massive concentration in the foreground, all the sources behind there are slightly tangentially distorted, because light rays are forced to make a slight detour in order to make it to our telescopes, and so that distorts the sky in this characteristic tangential pattern that you see there on the top right of the slide. So it's inherently very simple. It's a simple geometric thing you can look for in data, and it's based on what are in essence very simple imaging simulations of large parts of the sky. So also the data taking is in principle not very complicated. It doesn't require really sophisticated instrumentation. It just requires the ability to image large parts of the sky with great image quality. And so here's an example. This is just a small part of the sky from Hubble. The idea is that you take a patch of the sky like this and you look for these systematic tangential alignments of all the background galaxies that you see. So you can imagine taking a random point somewhere on this map and looking statistically whether the galaxies nearby have a tendency to be aligned tangentially around that point, yes or no. If the answer is yes, then that means that there is something in the middle of that area, some extra mass that's doing this kind of lensing. And so that's basically how you analyze the sky piece by piece, looking for these tangential alignments. So here's a simulation of how this works in practice. You take a large part of the sky, you chop it up into little cells, and then you basically measure the average shape of galaxies in each of these cells by averaging the ellipticities in a smart way. So you basically fit an ellipse to every galaxy, you look at the major axis position, you look at the axis ratio, and from that you get a statistical measurement of the average shape of the galaxies. Without lensing, this shape should be round. There's no preferred direction. Due to lensing, you will get a preferred direction and a preferred elongation, and that's the signal that you're looking for. So if you make a map like the one on the bottom left, where you look at the average ellipticity of galaxies as a function of position on the sky, using this two-dimensional potential theory, you can turn that into a distribution of mass that would cause this lensing signal, and that's what you see at the bottom right. So this is a simple mathematical transform from the shear field on the left to the mass field on the right. And this is all in 2D. You can make this even more powerful by adding a third dimension. If you have distances to all of the galaxies, to all of the source galaxies that you're measuring the shapes of, then you can do a kind of tomography. And that's what's shown on this slide. If you have a line of sight with lots of lenses along the line of sight, and you look at so 1, 2, 3, 4, 5, 6 are different lenses in this case, and you imagine that you're measuring the gravitational lensing by looking at sources at different redshifts, A, B, C, D, E. Then, for example, let's take the sources C. Then those are behind lenses 1, 2, and 3, and so what you measure at C is the effect of just lenses 1, 2. Sorry, I'm doing this the wrong way around. The sources are 1, 2, and 3, and the lenses are A, B, C. So look at source 3. Then that source, at that redshift, you're measuring everything in front of it, so between us and it. In other words, you're measuring the lensing effect due to lenses A and B, but not the things that are behind there, because the light rays do not pass there. If you then also look at source 4, for example, that's sensitive to A, B, C, and D, and so by comparing 3 and 4, you can disentangle how much of it is due to A and B, and how much is due to what's behind number 3 and A, B, C. And so this kind of slice-by-slice tomography is a way to peel off how much lensing is due to which part of the line of sight. And so that gives you, in the end, the three-dimensional picture of how the lensing effect is distributed along your line of sight with redshift. And so to be able to do this, you actually need to know something about how the distances relate to redshift, and so that means you have to assume a cosmological model to do this. So this is also a way of testing the cosmological model by looking at these geometric aspects of the lensing deflection. So in summary, we combine two things. We measure the shapes of galaxies to get the gravitational distortion, the shear. It tells us how much mass there is in front of those galaxies. And then we can do this as a function of redshift of the galaxies, and so add a third dimension. And in the end, reconstruct in some statistical way a three-dimensional picture of the mass distribution, and therefore the evolution of the clustering of galaxies. So until recently, until a few years ago, the state of the art was from the Canada-France-Hawaii telescope. So what's shown here are 4 of these mass reconstructions. These are now not simulations, this is real data. CFHT looked at 4 patches in the northern sky or on the equator, and these are the mass maps from these 4 different regions. This survey was well ahead of its time in some sense. The observations were taken between 2004 and 2009, but the first credible lensing analysis didn't really come out until 2013. And that's not because people were lazy, but because it's really it was a very long learning curve to learn how to reduce these data with the kind of fidelity that you need to bring out the lensing effect. It's really very complex and very technical work. So this is why the surveys that are happening now are able to benefit tremendously from this early pioneering work, and it's why really the time is right now to do this kind of work on a very large scale. so that was CFHT lens. And so what the situation we're in now, here again the CFHT lens mass maps. What came out last year was about a similar area, 140 square degrees from the dark energy survey, science verification survey. I think there's 139 square degrees plotted here. That's again a real measured mass map. I've tried to make them more or less to scale on the slide. And then what I'm going to be talking about later today is the 450 square degrees from the kilo-degree survey that we came out with this past summer. So in fact, the paper was accepted yesterday. So we have a lot more to work with now than with the CFHT lens, and this is only going to get better as these surveys continue. And so by contrast, these are the early measurements. In the early 2000s, this whole field started with the first detections of coherent ellipticities of galaxies due to lensing. And this was now on a scale of a few arc-minutes from very, very tiny fields. And it's actually quite amazing that this field has now gone so fast, really driven by the wide field cameras on large telescopes that we now have in multiple places on Earth. So the most recent measurements of this, what we call cosmic shear, so this correlated ellipticity of galaxies, are shown on this slide here. On the top right you have the correlation function of the mass map from the DES data. And on the left there's a different survey called the Deep Lens Survey, DLS, which was only 20 square degrees but which was quite a lot deeper. And so also actually samples a significant volume of the universe and is able to give you good constraints. So what's shown in both of these cases are two correlation functions, psi plus and psi minus, which are two different ways of combining these ellipticities into a correlation to look at over what scale ellipticities are coherent. Right, and I'll show you the KiDS results in a second. Here's a slide still on the 3D effect on the distances to highlight how important this is. So if you measure just weak lensing, you're only measuring angles on the sky. You have no physical quantity. To put the physics in, you need some quantity with a dimension, and that's given in the equation there. That it's really the ratio of the distances between us and the lens and between us and the observer that gives us this physical quantity, this physical distance. So you need a cosmological model to turn the redshifts into real distances, which is then what sets the mass scale for all the clustering measurements that you do. Right. And so getting these distances right is very important, because otherwise you will simply put in the wrong physical scaling and you will also get the wrong cosmology inference. So all that was to explain to you how simple lensing is. This is really conceptually, you're simply looking at the bending of light rays by gravitational fields, and that's it. Now, there's a lot of practical difficulties, which is why it's taken so long to get to the point where we are now. And so here's just a selection of them. The main one is that it's actually a very, very weak effect. We're typically looking at shears of about 1%, which means we're looking for distortions in the shapes of galaxies of about 1%. We expect the galaxies to get 1% longer in one direction and 1% shorter in another direction, typically, due to this lensing effect. And it can even be less. 1% is already a fairly strong effect. And galaxies intrinsically have ellipticities of about 0.2 RMS. And so you're looking for a very subtle effect on top of the random shapes that galaxies have. So you have to average over many galaxies, and you have to make sure that you don't have any systematic effects in your measurements, because otherwise you're going to get unreliable results. And one of the main things that affects this is noise. We're always trying to look at the faintest galaxies in our survey, because that's where most of the data are. And those galaxies are very noisy, and so it's actually very difficult to measure shapes. So in the postage stamp here you see models for typical galaxies that you would like to work with, but at unrealistically high signal to noise. Typically we have this kind of signal to noise to work with. And so you have to imagine that from images like this, and these are already quite good actually, this is signal to noise above 10, that in galaxies like this you want to measure in a reliable way, statistically unbiased, the ellipticity of these galaxies so that you can average them down to the point where you can securely detect average ellipticities of between 1% and 0.1%. So this is very complicated. This is what's taken so long to get right. One of the main nuisance effects is the point spread function, the fact that the shapes that we record in the images are not only due to gravitational lensing, but are dominated in fact by the seeing and by the optics. So the images are blurred by the atmosphere and by the telescope. And so you have to correct all that very carefully before you can get to the intrinsic shapes of the galaxies and pull out the lensing signal. You have to get the redshifts right, as I said before, to get the correct physical scaling of the measurement. And then you have to think about all kinds of other effects that might mean galaxies align their ellipticities which have nothing to do with lensing. And in particular, there's a tidal effect called intrinsic alignments, whereby nearby galaxies feel each other's gravitational field and that affects their shapes. And this can be something that can actually dominate the lensing signal, and it's something that you have to take care of in the analysis. So a little bit more on this point spread function. It really is true that if you take an image of distant galaxies, then the gravitational lensing effect, the shapes of galaxies are affected by the point spread function about 10 times more than they are by the gravitational lensing effect. So you have to get this PSF model really right to subtract it off properly and not leave any residuals. And this is difficult to measure because it's varying all the time, both because the telescope is flexing and changing its optical alignment, because the atmosphere is varying. And so fortunately we're able to measure this in real time because every image that you take contains lots of stars as well, several thousand per square degree. And so those are intrinsic or instantaneous samples of the point spread function, which you can fit very accurately and then use in your modeling to get rid of the effect that they cause. But still, how exactly you do this interpolation, how exactly you measure this is all complicated. You can also worry about chromatic effects in the optics and in the atmosphere, which is something that at the moment is only being done approximately. But for the next step, for example, for Euclid, this is going to become a very important thing to get right. Detector effects are also important to take into account. Typically, we assume that detectors are linear devices, but if you look at the physics of them, they really are not. And in particular, these thick CCDs that we use now, they can change their properties depending on how many electrons they've already recorded. So you get, for example, this brighter, fatter effect, that PSFs get slightly fatter for brighter stars. And so if you use bright stars as a PSF calibration, you'll get a bias that you have to correct for. All right, so lots of things to worry about. And so when you go to a lensing conference, you find in the coffee breaks half the people talking about PSFs. It's just something that's unavoidable in this field. Photometric redshifts are the other ingredient which is important to not make mistakes in. The requirements are also very tight. If you want to do precision cosmology, you're talking about percents, which means you have to get the redshifts right to the order of a percent as well in the mean. And also you have to understand the tails of the distribution and the distributions of your errors very, very well. So again, this is still something where there's a lot of research going on. It's by no means a solved problem yet. And I think this technique is keeping up with the needs of the surveys, but is certainly not ahead of them. So as more data gets collected and more accurate measurements are made, we have to worry continuously on improving this photometric redshift measurement as well. How exactly you measure the colors are an important part of that, but also what kind of templates you use, whether you do this with machine learning, etc., etc. A lot of work to be done there. So let me illustrate how we've tackled this in the KiDS 450 results that I'm going to show you. So the main thing, KiDS has a depth of about 24.5 in R, and that is just shallow enough, shall we say, that there are still deep redshift surveys that cover this magnitude range, and so we can actually try to calibrate these photometric redshifts directly using real spectroscopy. So no need for model fitting. So the way we do this is we get some initial estimate for the redshift of all the galaxies using BPZ, some photometric redshift code, and we split the galaxies into 4 redshift bins, and then we try to get statistically what is the distribution of the galaxies that we've selected in this label. So the real redshift distribution of these different samples of galaxies selected by approximate photometric redshift from BPZ. So this calibration happens by taking deep redshift surveys and reweighting the galaxies in them in such a way that they reproduce all the magnitude distributions and all the color distributions of the galaxies that we've selected in our BPZ sample. And so at the bottom there's an illustration of this. For example, if you look at the panels on the right, what you see there in red is the the distribution in colors, G minus R, R minus I, of all the spectroscopic, the deep spectroscopy that we have. And in blue you see the same sample of the KiDS survey, and so you see they're different. So one of these tomographic bins of KiDS has a different color distribution than the spectroscopic survey. And then what we do is we reweight all the galaxies in the spectroscopic survey until we reproduce the distribution exactly. And we do this for all the color combinations, for all the magnitudes. And so once you have this four-dimensional space well covered and well sampled, you can simply read off from your spectroscopic survey what the real redshift distribution of that sample probably is. And this works as long as you don't have too many ambiguities between different galaxies of the same color with different redshifts. So this is something that can get improved further and further and further, but for the moment we found that this kind of technique we do it very well. We validated it with a different technique, which is completely unrelated to these deep spectroscopic surveys, which is to look at cross-correlation. Here you don't need to get faint galaxies, you just need to sample the whole redshift, and then you look at what the extent to which galaxies cluster against spectroscopic galaxies at a particular redshift. If you find some clustering correlation, that means that the galaxies are likely at the same redshift. If you find no clustering correlation, then they're probably at different redshift. And so by correlating a tomographic bin with lots of different redshift slices from overlapping spectroscopic surveys, you can assess to what extent you have the correct redshift distribution as estimated before. And so what I'll show you here is 4 different slides for the 4 different tomographic bins. So the dashed lines, dashed vertical lines show you the nominal limits of the bins from the BPZ estimate, so 0.1 to 0.3 on this slide. And then the next ones will be 0.3 to 0.5, 0.5 to 0.7, 0.7 to 0.9. And what you see in red is a kind of reconstruction of the redshift distribution based on this cross-correlation technique. So you see here the lowest redshift bin from 0.1 to 0.3 indeed correlates mostly with spectroscopic redshifts at those low redshifts. And then if I go to the next bin, you see that also they correlate mostly with galaxies at higher redshift. Here's the next bin again, the 3rd bin now, you see that the peak moves up. And the 4th bin, the peak moves up again. So you see the distribution is different. There are galaxies outside this nominal range between the dotted lines, but nonetheless you see that the different tomographic bins do indeed lie at different redshifts, which is good. It means we can do tomography with them. And so on this next slide is a comparison between, if you look at the blue and the red, the blue was the direct calibration that I showed you first, so matching the magnitude distributions of galaxies. And the red is the cross-correlation technique that I just showed you. And you see that they agree very nicely. And so in the work that I will show you, we've been using the direct method, which is statistically more secure. But in future, when there are more surveys with which we can do the cross-correlation, this cross-correlation technique will be a very important part of the kind of techniques that we're going to have to use. So then there's one other aspect which you have to worry about, which is this non-gravitational lensing alignment of galaxies, these intrinsic alignments or tides. And that's illustrated here. So if you think that galaxies respond to each other's tidal field by changing their shape, then you might get something like what's illustrated at the bottom. If you have a wave in the density field, then galaxies that sit in that density field will get stretched or compressed depending on where they are in this wave. So things at potential minima will get compressed along the wave, and things at potential maxima will get stretched along the wave. So there's no gravitational lensing in here at all, but nonetheless here you have an effect which would cause galaxies to have correlated ellipticities, right? You see a very clear ellipticity wave in here. Now that's intrinsic alignment, which in principle you could filter out very quickly by simply not correlating galaxies at the same redshift. Then this effect would go away. But there's another effect which causes galaxies to correlate at different redshift, and that's much more difficult to get rid of. And that's illustrated with the green galaxies here. So let's now imagine that we're looking through this wave where the blue galaxies are at more distant galaxies. So those distant galaxies will be lensed by the same density wave, and so they're lensed in the direction that I show you. Like lensing works opposite to the tides. So at potential minima, which is where there are mass concentrations, you actually end up with a stretching due to lensing and magnification there. And so if you imagine now taking an observation from below, where you see both the lenses and the sources, both the blue and the red and the green galaxies, then this is what you see. And so you see now a clear correlation between the galaxies at different redshifts. Right? In this case, there's an anti-correlation in the ellipticities. And this again is not because there is a lens in front of both of the planes that's lensing both planes, both sets of galaxies. It's due to this correlation between the intrinsic alignment and the lensing effect of the background galaxies. And so this is something that you have to take into account when you do a tomographic analysis. This intrinsic alignment effect, or this intrinsic shear correlation, is actually one of the main nuisance parameters if you want to do this accurately. So again, also here we have to build models. It's not fully understood, so you have to marginalize over theoretical uncertainties here in the analysis. So then let's come to results with this kind of work. So typically what we measure is either the correlation function or the power spectrum of the lensing effect, so of the ellipticity field that we measure. And when you do this in a tomographic way, you're cross-correlating also the power or the ellipticities between different redshift planes. So if you cross-correlate the lensing effect between two different redshift planes, you're sensitive to all the lenses in front of the lowest of the two, and this is how you do the tomography. So you build this whole thing, you build you make a data vector out of this, you work very hard on getting a good cross-correlation, a good covariance analysis, and then you compare this to models which include both the cosmology, so the actual lensing effect that you're looking for, which is basically the power spectrum and its evolution with redshift, but also you have to allow for the redshift distribution of the galaxies. You have to allow for nuisance parameters like the intrinsic alignment that I showed you, like baryon effects on the power spectrum prediction, for example. And you can also decide to not fit all the scales, but only the scales where you trust your physical model the most. So you can play lots of experiments like this. And then this is the kind of result that you get. This is from the CFHT lens, which was reanalyzed at the beginning of this year. And you always get these kind of banana-shaped contours, which are combinations of sigma 8 vertically and omega matter horizontally, and that's because lensing is only sensitive to the amount of clustered matter, which is why it doesn't measure directly omega matter, or it doesn't measure directly sigma 8, but it measures this combination. You can either have a lot of matter which is not very clustered, or not very much matter which is very clustered, and it would give the same lensing signal. And so lensing basically only gives you constraints not along this banana shape, where you can have different results by changing the priors, for example, but it really only gives you constraints perpendicular to this banana in the thin direction, and that's what gives you this S8 parameter, which is a combination of sigma 8 and omega matter. And so what I'll show you later is really just measurements of this S8 parameter. So the contours on the right are the same data as on the left, but now plotted in terms of this S8 parameter on the vertical axis, and you see that it collapses the banana very nicely into a much more friendly shape. And the striking thing about these CFHT lens analyses results was that it doesn't overlap with the prediction from Planck. So if you take the Planck cosmology and you calculate it forward, you would predict more clustering than we actually seem to measure, at least with CFHT lens. And so this is what's the interest in this field at the moment, that there seems to be a suggestion that the late time clustering is not quite compatible with the early time clustering as measured in the CMB. And this could be a sign that the cosmology needs to be adjusted a little bit. So that was CFHT lens in 2013, and that really sets the motivation for doing these new surveys to see if these results go away or get more accurate or what happens. So here's a compilation from Martin Kilbinger last year of all these S8 measurements over the years. Many of these are the same data set analyzed in different ways, so all these data points are by no means independent. But what you can see is that there is a strong tendency for all these measurements from lensing to come out low with respect to the Planck prediction. Right? Basically, essentially no surveys get values higher than Planck, and many of them get values lower than Planck. So more recently there are these measurements here. There's the deep lens survey that I showed you before, which...
Hello?
Hello?
Oh,
so the deep lens survey on the top right shows you results which are more or less compatible with Planck. That's a very deep survey which has the problem that the photometric redshifts cannot be checked with spectroscopy because the galaxies are too faint, so there's some model uncertainty in there. CFHT lens has this problem to some extent, but less. It's not quite as deep, but wider. So that's the one on the bottom, which I showed you before. Top right is the DES science verification measurement, and again the CFHT lens results plotted underneath. The science verification measurements used didn't have quite as many galaxies yet to give a very competitive measurement, but you see it encompasses both the CFHT and the Planck measurement there, so it's not really conclusive as yet. And so what we came out with this summer is new results from the KiDS project based on 450 square degrees. So this is one slide on KiDS. These are the areas that we're covering. In total we're aiming for 1500 square degrees, and what we have in this analysis is the first 450, which is all the little symbols that you see in this map here. Meanwhile, we have almost 800 square degrees in the bank, so we're going to be starting the whole analysis pipeline soon to come up with results on the next measurements. So these are the results that we got. We've done the whole analysis in a blind way, so that we didn't actually know while we were doing the analysis what cosmology we were getting, just to keep ourselves honest and not have any kind of confirmation bias. So what we did was we took the shear catalog as we measured it from the galaxies, and then we made 2 copies of it which were randomly sabotaged by different distortion functions basically. And we analyzed all 3 data sets simultaneously, always comparing the results between the 3, but not knowing which of the 3 was the correct one. There was only somebody outside our collaboration who knew what the correct one was, and only when we were satisfied with our analysis did we ask this external person to please tell us the truth so that we could write our paper. So this was what we found in blind 1. You see some tension with Planck, pretty much consistent with the older WMAP cosmology. So the blue contours here are basically all the CMB constraints before Planck, so WMAP plus the ground-based experiments. That was one of the blind catalogs. The second blind catalog is the blind 2 here. By the way, in gray underneath is the old CFHT lens result. You see this blind 2 catalog is even more inconsistent with Planck. It's almost 3 sigma discrepant with Planck. And then the third blinding was consistent with Planck at the 1.5 sigma level-ish. So then we went and asked our colleague which was the correct one, and the correct one turned out to be the first one, the one that sat in the middle. So this one here. So some tension with Planck at the 2.5 sigma level or so. There's the S8 value that we measure at the top right, 0.745. And it's actually embarrassingly consistent with what we found before with CFHT lens. Many of the people in KiDS were also part of CFHT lens. And even so, the analysis is really very different, the data set is very different, the telescope is very different. Somehow we get pretty much exactly the same result. So you know, the only thing I can say to that is it's good that we did the analysis blind, so that, you know, that we cannot really be accused of having worked towards confirming the CFHT lens result. We tried lots of sensitivity analyses by checking the different ways of doing the photometric redshifts, by looking at ways of cutting out certain scales, by correcting for the tiny B mode in the lensing that we still find, and basically none of it can make it go away. So many of the things you might think of will actually increase the tension, if anything. So we're fairly confident that at the moment this is as good a job as we've done, as we're able to do. So if you look at this slide here where we see the kind of sensitivity analysis summarized, so this is this S8 parameter again, the gray band is our central result. And then in blue you see what happens when you do lots of systematics checks by switching on or switching off certain parts of the pipeline. And then the more interesting comparison is the green and the red, which are comparisons with real other measurements from lensing in green and from the CMB in red. And so you see there the Planck result at 0.85, which is the most discrepant and also in principle the most precise measurement of this S8 quantity. The WMAP constraint, the WMAP pre-Planck Calabrese et al. Result, which is perfectly consistent with what we find. The DES-SV, which spans both, the CFHT lens, which overlaps with KiDS, and then the deep lens survey, which is more towards Planck, but is is a much narrower, much deeper survey, and therefore you have to really worry about the photometric redshifts there. And so if we add this KiDS result to the compilation, you see that it again falls on the low side with respect to Planck, pretty much in the region where many other surveys before have landed as well. So, so what's next? So this is very interesting because if you think about the physics, we're measuring now directly the amount of clustering at late times and comparing this to the amount of clustering at redshift 1000. So we've actually got a tremendous extrapolation, a tremendous lever arm, and so I think point one is to say that we even get so close is an amazing triumph for the standard model, the standard cosmological model. But of course the fact that there's some discrepancy means that there might be something interesting there. So there's certainly, as far as I'm concerned, good reasons to keep on going with better and stronger, faster surveys to try to make this measurement more accurate. So the strengths of weak lensing are that you're able to access many modes, that you can largely sidestep galaxy bias, and that indeed in principle the measurement is very clean. Going a little bit deeper helps a lot because you quickly gain a lot more volume, which means that you're able to get a much more accurate measurement. On the other hand, you have to start worrying a lot about the redshifts then. So I think with KiDS we're sort of on the sweet spot. When we go to much larger areas, we really have to start worrying about this, these redshift errors. And so both more accurate shears and more accurate photometric redshifts are really setting the frontier for how well we can trust this kind of work. And I would say that, like with all of these large statistical analyses, having a blinded analysis is essential to keep you honest and to prevent strange confirmation bias and other weird things that human beings do. So in terms of the future, there are much larger surveys coming. So in that sense, certainly KiDS I view as a pathfinder, as a way of discovering lots of issues rather than making the definitive measurements. But once we have LSST, or then in space Euclid and WFIRST, we'll be able to make these measurements much, much more accurately, with higher fidelity, with lower systematic errors, hopefully. And so really push the subject forward with a much more accurate measurements when we will really know whether there is a serious discrepancy, yes or no. And not only the measurements from these large surveys are important, but also much of the astrophysics that comes in at some level in the models or in the intrinsic alignment or in the baryon effects in the power spectrum. All these things we will have to understand more accurately as well. And so specialized surveys like JPAS or POWs, which are really ways to measure the intrinsic alignment physics very carefully, or all the galaxy formation theory that's going on to try to understand the baryonic physics and its effect on the power spectrum. All these things will really be essential to be able to realize the scientific potential from these massive surveys. And of course, simply very banal, getting deep spectroscopic redshifts to calibrate photometric redshifts at large distance would also be very important. There's a whole bunch of things on lensing which I could have talked about but didn't, and I'm not going to now in view of the time. So let me put up my conclusions. Reiterating again that weak lensing is a very powerful tool. It's taken a long time to come of age, but I think now we're at the point where it's really beginning to bear fruit. Many of the technical challenges have been recognized and are being overcome one by one. In terms of physics, it's complementary to the CMB because we're measuring the large-scale structure at late time as opposed to early time. It's complementary to BAO measurements because we're really studying the growth of structure much more than the expansion history of the universe. So this combination is a very powerful, in principle, test of theories of gravity on large scales as well. And so the field at the moment is just advancing. There's ongoing surveys which are paving the way towards these massive space and LSST-based future projects. And that together with a better understanding of the theory of large-scale structure will mean we can really do some more precision cosmology than we already can. Okay, so I'm happy to leave it there and I'm happy to take questions.
Okay, thank you very much for your talk. So, questions? Any questions?
So, yeah, I have a question.
Hi.
So, can you hear me?
I can hear you fine, yes.
Okay, I was just wondering of this tension that you found And I did not go through the papers of the deep lens survey of the DLS or the KiDS paper. I want to know what are the differences between these two analyses, between the analysis of the DLS and the KiDS one, because I just saw that the DLS found something which is more consistent with the Planck results in your plot.
So, conceptually, the analyses are very similar. I mean, you're making the same kind of measurements and doing the same kind of analysis. So all the differences are in the details. And in terms of the details, almost everything is different. So the measurement, the way of measuring the shapes of galaxies and calibrating the gravitational shear is very different. And one of the things, certainly within KiDS, we put a lot of effort into is making lots and lots of simulations, many more simulations than we have real data, and putting in the shear and then testing our pipeline to make sure we get the right shear out, and we got this right to within 0.5%. I'm not sure exactly how this was done in the DLS data. I'm sure they were very careful too, but it's a different pipeline, different technique, so there might be a difference there. I think the biggest theoretical or the biggest systematic error that might affect DLS, which is really impossible to know whether it's a problem or not, is the fact that they go so deep to magnitude of 26, 26.5, that there really are no spectroscopic calibrations of the redshifts there. So getting the photometric redshift is absolutely essential to determine where vertically on this SA diagram you end up. If you get the redshift slightly wrong, then you overestimate the lensing signal or underestimate the lensing signal, and so you end up with a different estimate of sigma 8.
Yeah, maybe a continuation of the question, because I saw the first paper of the DLS, and they go through something of a cosmology-dependent covariance analysis. And I was just wondering if at the level of the KiDS analysis was done something similar or not.
No, we didn't. We used we sort of picked a central cosmology at the beginning and just did the cosmology, the covariance estimate for that. I don't think it's a big effect for what we're doing here.
Yeah, okay.
No, it might be an effect at the very ends of the banana, but those are not the interesting parts of parameter space.
Okay.
One thing I didn't mention actually is that we developed a new way of estimating this covariance as well, which is based on basically theoretical modeling in Halo model, rather than doing lots and lots and lots of n-body simulations and doing a kind of bootstrap way. We compared the two things and they were equivalent, but you end up with wasting tremendous or spending tremendous amount of computer time to do these mock simulations to get a covariance matrix. And it looks like we can do this more or less analytically, and also include supersample covariance, which you don't have in the mocks.
So you treated the covariance analytically?
We have both. So we had 1,000 mocks, which was how we started this project. But then as we were going through this, we also developed this analytic way of doing it, which gives pretty much consistent results, but is infinitely faster and more flexible, of course.
Oh, nice. I think I will go through the paper.
So in principle, with those, you might be able to make cosmology-dependent covariances as well.
Yeah, in principle, if you are computing analytically. So nice. Thank you very much.
Sure.
More questions? So I'm not sure if I understood very well. You used BPZ as the main code for PhotoZ?
No. So we do it we use BPZ just to place galaxies in different bins, to basically make 4 samples of galaxies, and then once we have those 4 samples, we calibrate the redshift distribution using these techniques that I discussed, but not BPZ. So BPZ is just an initial, if you like, an initial selection in color space to pick galaxies at different redshifts, and then we use different techniques to actually figure out what the redshift of those galaxies are.
Okay, but do you have differences if you had used machine learning techniques?
Probably. So we haven't applied those here. But you would get a different, different selections will end up with different error distributions, and therefore different galaxies will end up in different samples. So the point is, what we need simply for this analysis is groups of galaxies which are at different redshifts, so that the cross-correlation between their lensing signal tells you something about the cosmology. And once you have those groups of galaxies, you need a way to assess what their redshift distribution is. And that's where we use this direct calibration and this clustering technique. Using the BPZ for that would be very dangerous. We tried that too, and it gives you very unreliable results.
Okay, and so you have a smaller area compared to the dark energy survey, but you have more bands. How do you compare? What is better?
So actually, what I should say, maybe I was misleading, but what I presented today is based only on 4 bands, on UGRI. So we have not yet merged the infrared data into the photometric redshifts. We're doing that now, but that was not part of this analysis. So for now, we have UGRI, which we find is fine to this depth for making the tomographic bins that we need. The guess is that once we add infrared data as well, we will be able to make the distributions a little bit narrower, so we will suppress the tails by removing some of the degeneracies.
Okay, thanks.
But I think in DES there is no U band, right? There is Z and Y, but no U.
No, yeah, it's 5 bands, but not U.
Yeah, so I think that will also work.
More questions? Okay, so Anna, thank you again. So very nice talk. Thanks everybody for attending it, and see you all soon.